All right. Last class, we learned about a bunch of our subatomic particles, protons, neutrons, electrons. Our protons and our neutrons, those are the big boys. Those are the big ones, the massive ones. The semi-trucks, and electrons are the watermelons. They're small, little beans. Protons, the protons are in favor of. Positive. Protons are positively charged. Neutrons, the neuter part in the front looks like neutral. Neutrons are neutrally charged. And electrons, formerly negatrons, I don't know why they changed it, negatively charged. And we talked about what happens if we change some of those different subatomic particles, what happens to the particle that we have, the atom that we have, and worked our way up to getting to atoms and ions. So for the S2 minus ion, we can find the number of protons and electrons in that ion. We would start by looking at our periodic table and finding S. S is sulfur. Sulfur has an atomic number Z, atomic number Z of 16. So it has 16 protons. Some of you might be able to real quick do the math of if we have an overall 2 negative charge, that means we must have 2 more electrons than the number of protons we have, and your brain just says, all right, well, 18 electrons. For others of us, we might remember ion charge equals the number of protons minus the number of electrons. And we could plug in, we know it's a 2 minus charge because of that 2 minus that's floating in the top right corner behind the sulfur. So we fill in a 2 minus charge for the ion charge. We figured out our number of protons is 16, and we can write whatever we want for number of electrons, just as long as it's some symbol, and then we can solve for it. So one of the issues that we've got right now is that we're subtracting x. We want x to be positive and by itself. So we could multiply both sides by -1. That gets us to 2 equals -16 plus x, or x minus 16. Then we could add 16 to both sides to move the 16 over. And we get 16 plus 2 equals x, or 18 equals x. So we have 18 electrons. You might choose to rearrange it a different way. You might choose to just plug numbers in and see what makes that statement true. It's not that crazy of an algebra problem, so if you wanted to just plug numbers in, that works. Questions about doing that stuff? Excellent. As I mentioned before you started lecture recording, this is a lecture you're going to want to have out your yellow sheet, your green sheet, because we are going to be learning some names. And your green sheet is your helpful hint for some of those names. On our periodic table, we've got numbers. They're 1 through 18. Let me write that in ink. 1 through 18. That's how we have them labeled in the class. That's how they're labeled on our yellow sheet. Other places you'll see them labeled with an A designation, like 1A through 8A. These A's mean that we're talking about our main group of elements. That also corresponds to the number of valence electrons. Valence electrons came up in a comment last class. So that's the number of our valence electrons. Valence just means it's our outer shell. So spoiler alert, the way that atoms are set up, they have different layers. You can think of them like onions or ogres or cakes, right? They've got different layers. And our outside layer that's our valence layer. Valence just means outside. So our outermost layer can have somewhere from 1 to 8 electrons, and that corresponds to the column that we're in. There's a shortcut if you don't have the A designation on the periodic table. Just look at the number in the ones place. So for our group 1, our alkali metals with hydrogen at the top, that's 1A. With beryllium Be, that's 2A. Skipping across to B for boron, 13, that's 3A, so we just chop the 1 off in front. Carbon's 4A, nitrogen 5A, and so on and so forth. And this is helpful because of this second main group elements. Those are in the 1A through 8A groups, excluding that rectangle in the middle of the periodic table. Those tend to form ions that have the same number of valence electrons as the nearest noble gas. Column or group 8A/18. So our very last column or group or family, those are our noble gases. And our main group elements are going to form ions that have the same number of valence electrons as those noble gases. An important note here, some of you have flown on a plane before. Where are the emergency exits? Sometimes they're in front of you, sometimes they're behind you. The emergency exits may be located behind you. It's the same way, same thing for noble gases. The emergency exits, the noble gases, might be behind you. So for example, if we're looking at potassium, K, the nearest noble gas is not running all the way across the row to krypton. It circles back from K to Ar, argon. So argon is the nearest noble gas to potassium. So nearest noble gas may be behind, up a row. All right, if we group some atoms together, let's say that we've got sodium metal. Sodium's a soft silvery metal, kind of dull. It reacts violently with water. Chlorine gas is a yellow gas, not something that you want to be smelling. You can combine those two elements together to produce table salt. And our chemical formula is based on the elements. So if we combine sodium metal and chlorine gas together, we would have this NaCl as our chemical formula. Our chemical formula shows us what elements are present, so which of our different flavors of atom on our periodic table, which of those are there, and how many of each there are. So for example, this CH4 that we have here, this is methane. That's the natural gas that you cook with on the stove at home if you have a gas stove. We have carbon, represented by the C. We've got hydrogen, represented by the H. And we have different numbers of each of them. So carbon, for example, has no subscript after it. Anytime there's no subscript, we assume that it's just 1. If we wrote in all of the 1s, it would start to get a little bit clunky and messy, and also chemists love saving a little bit of time in the most meaningless ways. So that's a way that we can save a little bit of time and make things a little bit clearer for ourselves. So 1 carbon, and the hydrogen has a 4 after, that means we have 4 hydrogens. And the subscripts always trail. Or follow the element they're talking about. We'll be looking at a lot of chemical formulas. It's an easy way to represent chemicals. Sometimes our chemical formulas are more complicated. A lot of the time they're more complicated. So they might have groups that act as a single unit. We call these polyatomic ions. The poly, of course, being many, and ions if they have a charge. So polyatomic ions are things that have a charge. You've got a bunch of polyatomic ions on your green sheet. And it's important to us, it's important for our knowledge, for the way that we read the chemicals, that we see that it's, for example, here PO4. If we wrote it instead as P2O8, if we distributed this 2, P2O8 would imply a different thing to a chemist. So it's a different way of representing the information. It means something to me, and it will someday mean something to you, I hope, as well. So breaking down the chemical formula that we've got here. We've got our calcium, Ca. We've got a subscript of 3 trailing behind it. That means we've got 3 calcium atoms. And then we've got parentheses. The parentheses mean that everything that's inside of here is 1 unit, and the subscript that follows it, this 2, applies to this group. We've got 2 PO4 groups. So 2 PO4 groups. In each of those PO4 groups, we've got 1 phosphorus, and we've got 4 oxygens. So we can count up our total. We've got our 3 calcium atoms over on the bottom left, right? 3 calcium atoms. We've got the subscript of 2 outside our parentheses times the 1 phosphorus that we have inside. So 2 times 1 is 2 phosphorus atoms. We do the same thing for the oxygen, the 2 times 4. We have a total of 8 oxygen atoms. Do we have any questions about how we counted that up? We'll be doing this a lot, counting those up. So it's important that you get it down as a reflex of being able to figure out what's going where. It's usually going to be simple, relatively simple multiplication like this. It's always going to be whole number stuff. So that's one example of an instance where we might have a more complicated formula. Another important note, those subscripts are very important. So we're never going to be swapping the subscripts unless we mean to talk about a different chemical. As an example, CO is the formula for what we call carbon monoxide. That's very bad for you. Breathing in carbon monoxide has some like short-ish term health effects. It can cause you to pass out. CO2 is relatively harmless. CO2 is carbon dioxide. These are different chemicals because they have different subscripts. Carbon dioxide, relatively benign. We're breathing it out. It's all around us. Not as big of a deal to be breathing in or out carbon dioxide, whereas carbon monoxide, bad stuff. So changing the subscripts changes the chemical. There's a dumb joke about this. Same idea. 2 chemists walk into a bar. The first one says, "I'll have H2O2," or "I'll have H2O." The second one says, "I'll have H2O2." They both drink their drinks, and the second one dies. Because H2O is water, H2O2 is hydrogen peroxide. Not what you want to be drinking. Obviously, that didn't happen because, you know, who's got hydrogen peroxide on tap? All right, for our chemical formulas, we've got a couple different options for chemical formulas. One of our options is a molecular formula. A molecular formula corresponds to a molecule. We'll learn what a molecule is in a little bit. But a molecular formula says the actual number of atoms in each unit. A molecule is a type of unit of chemical. So our smallest unit, little building block, is the molecule in some cases. Glucose, for example, is a sugar molecule. Every molecule, every smallest unit of glucose is going to have within it 6 carbons, 12 hydrogens, and 6 oxygens. That's our smallest unit of glucose, similar to how an atom is our smallest unit for an element, any of those 118 on our periodic table. There's another type of formula called an empirical formula. And an empirical formula gives the relative number, not the actual number, of atoms in a compound. Empirical means not relating to empire, but in our case it means experimental or experimentally determined. We'll do a lab where we come up with an empirical formula. So hopefully that'll help us see why there's some value in learning about empirical formulas. So for example, for glucose, each of our subscripts, the 6, the 12, the 6, we can divide those by a bunch of numbers, but we can divide them by 6 to get CH2O. This is our simplest whole number ratio of elements. That's why we divided by 6, so that we would get to the smallest possible numbers. So relative to each other, we have 1 carbon for every 2 hydrogens and every 1 oxygen. This empirical formula could also describe other things other than glucose. If we multiplied our empirical formula by 2, for example, this could refer to C2H4O, which might be a real chemical. It doesn't just refer to glucose necessarily. Sometimes our empirical formula and molecular formula can be the same. So for example, for water, we've got an implied subscript of 1 after our O. So that means that we are in our empirical formula. It's the simplest ratio of elements that we can get. Ammonia, NH3, also has an implied subscript of 1 in it, so that means that it's an empirical formula. And sucrose, different than glucose, but also a sugar, has an 11. You may know that 11 is a prime number, so we can't divide that by anything other than 11. And this 12 can't be divided by 11, so that's also an empirical formula. So these are all the simplest whole number ratios, and they are also the actual number of each of those elements in that particular chemical. There's a few ways, lots of ways, that we can separate or group our types of chemicals that we have. One of our types of chemicals is elements, things that show up on the periodic table. Not all of these show up with an atom, a single one of those things, the smallest unit, by itself. Lots of them do. So atomic elements have their smallest unit of 1 atom. However, some of our elements also fall into a second category of molecular elements. So multiple atoms bonded together. And that's how they normally exist. You're more likely to find them, you're most likely to find them as multiple of the atom linked together by a chemical bond. Joined at the hip, if you will. We're going to learn some that are diatomic. The di meaning two. So we've got a bunch of diatomic elements. So these exist as two atoms bonded together, and they're labeled here on this table: hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. There's multiple mnemonics, multiple devices that you can use to remember those. So one of those is Brinkelhoff. So that's the first one here. Brinkelhoff, bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, fluorine. So you can remember Brinkelhoff if you'd like to. It's kind of silly, it's a little bit nonsensical, but that's one of the mnemonic devices. That's the spelling for mnemonic, in case you were wondering. I'm sure you weren't. And then another one of them is H7. So if we look at our periodic table in the class, hydrogen up in the far top left corner. And the rest of these, nitrogen, oxygen, fluorine, down to chlorine, bromine, iodine, form kind of a 7 shape. Like if you have an older digital clock, it might form the 7s with that sort of loop shape. So our H, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. Looks kind of like a 7. And then the last one, which is my favorite, horses need oats for clear brown eyes. And the eyes being the letter I instead of like the ones that are in your face. So horses need oats for clear brown eyes. Each of these starts with the symbol for one of our diatomic elements. Now, I'm not much of a horse girly myself, so I don't know if that's true. But it's a convenient way of remembering, potentially, the diatomic elements. So there's 3 possible tools you can use to remember your diatomic molecules, diatomic elements. And then everything else, for this class at least, we can just assume is atomic. It's just one atom by itself. It's not 2 or 5 or 7 or some weird number. So that's the way we can break down our elements. We also have compounds where we mix our elements together. So multiple different elements, but together, rather than just one element. We've got 2 types. We've got molecular compounds. These form molecules. And molecular compounds are formed from 2 or more nonmetals. Who remembers where our nonmetals are on the periodic table? Mostly. So if we imagine that diagonal line in there, our diagonal line is our semimetals or our metalloids, and up and to the right, the top right corner, that's where most of our nonmetals live. Hydrogen would also be considered a nonmetal. And then we also have ionic compounds. These contain 1 or more cations paired with 1 or more anions, and usually for this class pretty much always contain a metal. So ionic compounds, you might memorize metal plus nonmetal. As a reminder, in case you don't have perfect retention from last lecture, I'm guessing that's most of you, Cations are positively charged. Anions are negatively charged. So we'll have a positively charged ions. We'll have negatively charged ions. So those cancel each other out. And we're typically going to have a metal in there as well. So sodium chloride would be an example of an ionic compound. We've got sodium. Sodium's a metal. We also have chlorine. Chlorine's a nonmetal. Ammonia, by contrast, only nonmetals. Don't be putting any metals in my molecular compounds. Only nonmetals. Questions about those two distinctions so far? Okay. More on ionic compounds now. So our ionic compounds are a metal and a nonmetal. We talked about that on the previous slide. And our smallest unit, our basic unit, is the formula unit. The reason that it's a formula unit and not a molecule is that if we look at this representation of sodium chloride, our sodium, I think, is our greens here, and our chlorines are the purples. It doesn't really matter which. And you can see we've just got like a lump of them sitting next to each other. We've got an alternating array of sodiums and chlorines and sodiums and chlorines, and that's going on in every direction. This is how ionic compounds are formed. It's a massive array of them rather than being discrete little units. Like in a molecule, if you have a molecular compound or a molecular solid, you'd have the same unit and just stack another unit on top of it. Stack another unit to the side of it. Whereas this is a continuous pattern of everything that's in that compound. And this is why on our last lab, or experiment 1, for the salt that we had, barium chloride's ionic, and in the solid form, it's this big repeating array. When you dissolve it, the water molecules pull those apart from each other. So it's actually a different thing when it's dissolved versus when it's in its solid form. So our smallest repeating unit is the formula unit. So rather than trying to count up how many of each there are, we just say this is our smallest repeating unit, and that's good enough for us. Otherwise, the numbers would get ridiculous. All right, we have 4 substances here. Let's classify them as either an element or a compound, and then we can further divide those to atomic element or molecular element, molecular compound, or ionic compound. I'll give you about a minute to maybe discuss it with your neighbor. All right, that was about a minute. For our first one, we have Fe. Is that an element or a compound? It is an element. It shows up on our periodic table. We can also tell from the formula we've got a capital letter and a lowercase letter. That means it's just one element. Our capital letters are the start of our element symbols. So we've just got one element symbol. That's iron. So it's an element. Is it an atomic element or a molecular element? It is an atomic element. How do we know it's an atomic element? It's not that it's naturally occurring. Yeah, it's not part of our H7, our Brinkelhoff, our Horse's knee notes for clear brown eyes, whichever one of those you prefer. Or if you want to use none of them and just brute force memorize them, that works too. So not in Brinkelhoff. I think that's the fastest to write. No, H7 would be, but whatever. All right, next one up. Cl3. Is that an element or a compound? It's a compound. How do we know it's a compound? That's right. We have multiple elements. We've got P, phosphorus. We've got Cl, chlorine. And is that a molecular compound or an ionic compound? It's a molecular compound. We know that it's a molecular compound because I told you, but also because P and Cl, phosphorus and chlorine, are both nonmetals. If you're not clear on the distinction, you might have guessed that it was an ionic compound, but it's like right next to the like the metalloid line, not really in the definitely a metal zone. So hopefully you got that that was a molecular compound. Next up, LiBr. Is that a compound or an element? This one's also a compound. And is it a molecular or ionic compound? This one is ionic, and we know that it's ionic because lithium is a metal. Bromine, Br, is a nonmetal. Metal and a nonmetal makes an ionic compound. And last but not least, oxygen gas. Is that an element or a compound?
It's a molecular element.
It's an element, and it is a molecular element. We know that it's a molecular element because it's in Brinkelhoff. It's the O in Brinkelhoff. Or it's the oats of Horse's knee oats for clear brown eyes. Questions about any of those? All right, we're having fun. Okay, so ionic compounds have ions in them. When we're talking about ions, there's a couple options. We've got ions that have predictable charges. We like ions that have predictable charges. Ions that have predictable charges include, for metals, things that are group 1A, 2A, or 3A. Those form very conveniently +1, +2, +3 ions. So we're talking about hydrogen and everything below it, beryllium, everything below it, boron going down to probably gallium, but we might throw indium and Tl in there as well. So those metals are going to form the same charge every single time. We've also got a couple of weird ones. We've got zinc and silver. Zinc and silver, Zn and Ag, show up in our transition metal elements. Our transition metal elements generally don't form the same charge every single time. They have multiple options, and that's part of what makes them weird. The way that I remember the zinc 2+ and the silver is there's a little staircase where aluminum is on this top step. Aluminum's in our 3A. We know that aluminum's going to form a 3+ charge. If you step down one step, you get to zinc. Zinc is a 2+. If you step down one more step, that gets you to silver. And that has a 1+ charge. So that little staircase, I think, is nice for remembering those charges. You could also just remember they're 1 over, but you wouldn't want to get cadmium and copper mixed in there because they form multiple charges. For our nonmetals, so things more on the right side of the periodic table, nitrogen and over, those are typically going to form a charge that is their group number minus 8. And this is the A designation group number. Or you could also count how far they are away from group A. So for nitrogen, for example, nitrogen we need to move over oxygen, fluorine, neon. That's 3 spots to be in the noble gas column. So it's going to form a 3- charge. Sulfur is 1, 2 spots, chlorine, argon, from being a noble gas. And so that's going to form a 2- charge. All of our halogens are 1 spot over from being a noble gas. So gaining 1 electron, they're a 1- charge. That works for all of our nonmetals. Another note about our ionic compounds is that they have to contain positive and negative ions. The chemical formula will be neutral. So 0 charge. So we have to have our positive charges and our negative charges perfectly balanced, like all things should be. Ion questions? I'm a lecturing machine. I'll just keep going unless you stop me. Okay, here's looking at those things on the periodic table. This might be helpful. You could maybe you could take this slide, erase all of the ones that you see here, fill in all the other boxes with black or get rid of them, and then play a game where you fill them in. Just print out a blank version of this, fill in all the elements that you can, refer back to here. Okay, what did I miss? Try it again. Just do that once or twice a day. You'll have it down in no time. So here we can see far left are 1A, our alkali metals. These all have a 1 positive charge. Just slightly further over to the right are alkaline earth metals, alkaline earth being longer than alkali metals. Those are all forming 2 positive charges. In our 3A, we've got aluminum forming a 3+ charge. We can see our staircase stepping down to zinc, 2+, stepping down to silver, 1+. And we also have in our nonmetals area our 5A that form 3-, our 6A that form 2-, and our 7A that form 1- charges. The expectation for this class is that you know all of these. It's not like really that many to memorize if you know the 1A, 2A, 3A, and you can count from 5A over to getting to this 8A column. Once you get the hang of it, like once you get to an advanced level, you see the element, you know exactly what the charge is going to be. Until you get there, maybe a little bit of pain, maybe a little headache. Some people like to write on their yellow sheet what the charges are. That might be helpful, but also if you get in the habit of always having it given to you, then when you get to the exam, I don't write those on your information sheet, so that might become problematic. When we're writing out formulas for compounds, you might be given the 2 types of ions that are in the formula. So for example, I might tell you we've got magnesium and we've got chlorine, and we're forming an ionic compound from those 2 elements. So what we would want to do is write out the symbol for both ions. That means we include their charges. So magnesium we find in our 2A column. It's number 12. It's in the 3rd row. It's in the 2A column or the 2 column. So that's going to be magnesium 2+. Then we would go and find chlorine. Chlorine's in our halogens, our 7A or our 17. It's also number 17. that means it's going to form a 1 minus charge. It just needs to bop over one spot to be a noble gas, so it forms a 1 negative charge. So there's our symbols with the charges. And then you can either, if you're good at quick maths, make the positive charge and the negative charge balance each other. If you can do that in your head without any instruction, great, awesome, do it. I'm thrilled if you can do that. You don't need to show me that you can do it. I'll trust you that you can do that. However, if that seems a little daunting, there is another method, and that's the crisscross method. So we're going to take our Mg2 plus, our Cl minus, and we are going to cross and criss the numbers that we get. So this 2 from the magnesium is going to be the new subscript for chlorine, and the 1 minus on chlorine, is going to be our new subscript on magnesium. So this would turn into Mg with an implied 1 and Cl with an explicit but PG rated 2. And that would be our formula. Sometimes we'll get something with these subscripts that we can reduce. So an example of that, if we've got something that can form a 4 plus charge, like lead, source, trust me. So let's say we've got lead 4 plus and sulfur 2 minus. If we crisscross these, that'll turn into Pb2S4. Since it's an ionic compound, it's this everlasting gobstopper repeating array of all the different ions, and our formula unit is the simplest ratio. So we need to make sure that this is the simplest ratio. 2 and 4 both divide by 2, so we would simplify it down, and we would get not B, P, B, S2. And that would be the correct subscripts for that ionic compound. Again, if you can just do it in your head, you see 4 plus, 2 minus, okay, 2 minuses equals the 4 plus, but opposite, right? You can just pop a 2 in for the S subscript, and then you don't have to deal with simplifying. And then the last thing that you might want to do is just check and make sure that your charges cancel out. So an example, we're going to do this for aluminum and chlorine. We'll find aluminum on the periodic table. I know that aluminum is Al, so we can find Al on our periodic table. It's in group 13. If we chop off that 1 in front, 3A. 3A means 3 plus, so aluminum 3 plus. And for chlorine, I know that chlorine is Cl. We can find that on our periodic table as well. It's in the top right-hand corner. Cl, it's in 17 or 7A. It's one spot from being a noble gas, so that's going to form a 1 minus charge. And then you can either do it in your head and come up with the formula, or like we're going to do here, we crisscross them. So a subscript of 1, again this is implied so we don't need to write it in, on our aluminum. And our chlorine gets a subscript of 3. Then we would check, can we reduce this? We've got a 1 for a subscript, you can't reduce a 1. We've got a 3 for a subscript, you also can't reduce a 3 unless it's the smallest sometimes. So this is fine. So we've got our simplest subscripts. Great. And then what we can do to check that the charges balance out, we take the subscript times the charge and see if that equals the subscript, that 3, times the charge on chlorine. 3 times 1 equals 3 times 1. We did it. If you want to include the positive negative, you can do that. Questions? All right, write a formula for the compound that forms between sodium and sulfur. I'm going to give you a couple minutes to work on this. All right, coming up with a formula for this compound between sodium and sulfur, we would need to first track down sodium. Sodium is one of those ones that has a symbol that's based on an older name, natrium, Na, and sulfur, very conveniently, just S. So we'd find our little NAS up here on the periodic table. Na is going to be in that group 1 or 1A. So our charge is going to be what? 1 plus. And sulfur, S, is in 16 or 6A, and so that's going to have what charge? 2 minus. Now you might immediately see, okay, to balance that out, Na2S, or you go ahead and crisscross it. We get Na2S. That S having an implied subscript of 1. And then if we wanted to check the charges, we could, but I trust myself here. Questions? Yes?
So when you crisscross it, turn it into a positive, -2?
The subscripts that we use, we toss out the positive negative. We're just using the number part. Other question?
Why is the S after Na? Why do we do Na2S instead of S?
So the order of the elements, there's, I think, an official order that they go in. Generally, it's going to be the most metallic thing first, and then decreasingly metallic things after it. So metal first, non-metal second. You're always going to see that. When we're working in molecular compounds that are all nonmetals, the order, there's an established like hierarchy of what gets to go first. But usually it's just like something that you learn by doing, rather than memorizing a list of like the exact order of 15 different elements. As fun as that would be. Other questions? All right. We can also do stuff with polyatomic ions. Remember, our polyatomic ions are a group of ions, or a group of atoms. That's the polyatomic part. Many atoms with an overall charge. The polyatomic ions stay together as a unit or bunch. Not that. Here are just a small number of polyatomic ions. Your green sheet, if you're looking at the side that doesn't have the solubility table on it, on the top you've got oxyanions. Below that you've got some rules about oxyanions. We'll be going through that. Then you've got some other naming rules, and at the bottom, common polyatomic ions. If you look at the information sheet for exam 1, you'll see that a lot of this is there. I'm not expecting you to have it perfectly memorized and nailed at this point in the class. It'll help you out a lot later in the class, like further in the class, if you get these rules down. If you start to memorize some of these ions. So let's say that we want a formula between the compound formed by calcium and nitrate ions. This 8 ending is indicative of being a polyatomic ion. For now, that's all the information that we can gather from that 8 ending. So we've got calcium. I believe we've already seen calcium as a 2+. And nitrate, we could go to our table and we would find nitrate, NO3, and that whole group, that NO3, has a 1- charge. So we can crisscross this, just like with other things. The important thing to note is that when we're crisscrossing these, this 2 that we're going to put on our nitrate applies to the whole nitrate. So we have to show that that's separate and put parentheses around it. So this would turn into Ca, open parentheses, NO3, close parentheses, 2. You might be able to imagine if you didn't put those parentheses there, that 2 could get confusing. So for example, CO3 or CaNO3 2, which is not what we have. We don't have 32 oxygens. And another way that you might do it is you might multiply that 2 across, but it's actually more helpful to have it separated, because when I see this NO3 in those parentheses as a chemist, I know that's a nitrate group. I have the name for that on my brain ready to go at any time. If I say CaN2O6, I'm not sure off the top of my head what N2O6 would be. So this is actually a value-added formula, having those parentheses there. That's helpful, and you want to do that. Another example, we can write a formula for the compound that forms between aluminium and phosphate. Again, we've got that 8 ending. 8 means polyatomic. So aluminum, we find it on our periodic table again. It's in the 3A, so it's aluminum 3+. Phosphate, we can find on our green sheet that's up in that top section, oxyanions. Phosphate is PO4 with an overall 3- charge. Hopefully, you can see that we've got a 3+ and a 3-. If we just combine those 1 to 1, the charges cancel out. That's the fastest way to do this one. So Al PO4. If you want to crisscross it every single time, you can do that. We would get Al subscriptive 3, open parentheses, PO4, close parentheses, subscriptive 3. And then we would simplify to, you guessed it, AlPO4. Two ways of arriving at the same destination. How are we feeling about this? Do we want to do a practice exercise? A couple of people are nodding yes. Best of luck to you. I'll give you a little bit of time. All right, coming up with our formula for the compound that forms between potassium and sulfite ions. This "ite" ending is also indicative of polyatomic. It's a little signal. It means more than just polyatomic, but for us, for now, that's all the information we can get from it. So we'd also need potassium. Potassium is K from kalium. So potassium, K, showing up in group 1, that's going to be a 1 positive charge. So K plus and the SO3 2- that I gave you. We can crisscross it. We get K2, that's me, SO3. I'm the second born, that's why I'm K2. Questions about the chemistry? Comments? Smart remarks? All right. Why are we learning all of this? We're learning all of this for nomenclature. Nomenclature, I think, is probably one of the two words in chemistry that makes chemistry students maybe not quiver, but feel a little bit of trepidation, a little bit of unease. Nomenclature is just naming. The name for nomenclature comes from something about a list and like crying. Crying like somebody selling a newspaper on a corner, but it can feel like the crying boo-hoo, weeping sort of sad when we're learning it. So I think crying list is a very apt origin for this name. So nomenclature is just how we name things, how we name different compounds. And we've got different naming systems. We are going to learn 3 different naming systems. We're going to learn the simple versions of these naming systems. It gets way more complicated. We're not going to learn that. So we're going to learn the simpler stuff. It's still going to be a lot. It's going to feel like a lot. That's understandable. But we're going to go through it, and hopefully you'll be able to make sense of how we're naming things. The big part of naming things is identifying the type of thing that we're naming. The type of compound that we're naming changes how we name it. Another note is that some compounds, many compounds, have a common name. Modern chemistry, we use the common names less. There's less of like, oh, this is Morton's reagent, and then you just have to know what Morton's reagent is. They're more of a system that you can follow like stepwise. You just memorize a procedure, and then you can come up with the name or come up with the chemical formula instead of Morton's reagent. Who was Morton? What was that chemical? I don't know. I just made it up, I think. So some things like water and ammonia, they have a common name that we'll often use instead of the systematic name. Again, our first step in naming is identifying what it is we're naming. So if we're naming an ionic compound, we need to identify it as an ionic compound. An ionic compound is a metal and a nonmetal. And this is true most of the time. That's another thing that's frustrating for some people about chemistry is we've got lots of rules and there's lots of exceptions to all of our rules. So like, what's the point in having the rules? It is helpful, trust me. So if we have compounds that have this NH4 plus group, ammonium, that will show up at the front as NH4. Those can also be ionic compounds because we have a positive charge on the ammonium. I don't think that I've ever put ammonium on an exam. So I keep it simpler, metal and nonmetal. I think in the homework, you'll see ammonium show up. So you'll still have to identify that it's an ionic compound based on the ammonium. On exams, we keep it simple, metal and nonmetal. Once we've identified that it's a metal and nonmetal, we can categorize that into 2 different types. So we have options of cations that have 1 charge possibility, cations that have 2 charge possibilities. Who knows what a cation is? Who remembers?
Positively charged ion.
It's a positively charged ion. So our positively charged ion, like a metal or ammonium, those can either have 1 possible charge or more than 1 possible charge. We've talked about the ones that can have 1 possible charge. And for the ones that have only 1 type of cation, here's the little relevant sections of our periodic table. That's our 1A, 2A, 3A aluminum, and stepping down to zinc and silver. When we are naming these, we call the ion the element name followed by ion. For example, lithium ion. That's Li plus, rather than just lithium, which would be Li. So we're adding the ion. The ion means it's charged. And lithium only forms one type of charge. And we know that we're talking about Li plus, not some weird Li2 plus that could exist. So these are the simpler ones. We can also have metals that form more than one type of cation. And these are, by and large, transition metals. So this rectangle in the middle from scandium to zinc and everything below it, except for zinc and silver, those are not always the same charge. So our transition metals, but not zinc and silver. Those can form multiple charge possibilities. It's a great time to be alive for learning this nomenclature. Thank you, Alfred Stock. So we use the modern Stock nomenclature. I'm going to talk about the other nomenclature, which is awful. So the name of the ion is the element name, followed by the charge in Roman numerals in parentheses. So Fe2 plus, 2 plus in Roman numerals is II, captain. And Fe3 plus is a whole mess. FeIII, right? Iron III. If you've forgotten your Roman numerals, or you just never learned them, we shouldn't go up to 10, but it's III, IV, V, VI, VII, VII, IX, and X. We're typically going to stay 6 and under. So good stuff. So here's a look at a table of some of the options, not all of the options. And I'd like to point out, we've got our modern name, that's Stock nomenclature. Thank you, Alfred Stock. Where our name is iron and the charge in Roman numerals after it. The old nomenclature, which I'm mentioning just because you'll see this in some older books or some older papers, it does show up places, is this OUS and IC ending. So for example, iron 2 plus is ferrous ion. And you might think, okay, great, all the 2 pluses are the OUS ions. You would be wrong. You would be sadly mistaken. So copper 1 plus is the cuprous ion. And then the cupric ion is one more. And then we also have plumbus and chromis and stannous and lots of other ones. There's probably tinnus. No, stannic is tinnus. There's lots of them. And you would have to memorize at least one ion for every single one to get the names correct. So if you see this nomenclature, if you see these common names, just Google it. Just look it up on Google. Don't bother trying to learn them unless you really want to. You don't need them for this class. Great time to learn this nomenclature. We, in this class, don't use these. They don't exist. So that's nice. So that's our cations, the positively charged things that would be in front. The back side are the anions, the negatively charged things. So monoatomic anions, just one atom, an element. And when we have a single nonmetal element, we change the ending of the name to "-ide" and add ion. The ion, in my mind, the ion part is optional because the IDE ending already means that we're using an ion. So some of these, like fluorine, would be the name. The base, fluor, and we change that instead of ene, it's ide, so fluoride. An important note for my sanity. What's the first vowel in fluorine or fluoride? It's me. Wait, it's you. F-L-U-O. It is not fluoride. So I beg you, please, for my sanity, it doesn't really matter. It doesn't really matter, but I can't convince my brain that it doesn't matter. So when we get to the nomenclature worksheet, fluoride, not fluoride. Please, thank you, please. Some of these are also not necessarily going to be the most intuitive. Sulfide, phosphide, we'll see some other ways that those change that are possibly confusing. Okay, so again, we're learning a simplified version, and we'll probably just have time for the ionic parts. So ionic compounds in this class, 2 ions. We've got a positively charged ion, a negatively charged ion. The real world is more messy. You can have multiple cations, multiple anions, you can have mixes. We're ignoring that. We're pretending it doesn't exist. So the name in our class, the name of the cation, like almost did it, iron 2, if we have Fe2+, for example. And if that's combined with chlorine, chloride. So name of the cation followed by name of the anion. It's pretty simple. It's the iron 2 because iron can form multiple charge options. If we mix sodium and chlorine, sodium only forms 1 charge, so we don't specify what charge it is because chemists know sodium forms Na+, so we don't have to specify. So only 1 charge option. So we don't specify. So these are a couple of things that we can name. This is an example one, so I will go through it and show you the way. These are things that just form one type of cation. Very convenient. Our ion for calcium, Ca is calcium. Calcium always forms a 2+ charge, only 1 charge option, so we just write calcium. Nice. And then the chlorine. The chlor part, that's the base, and we change the ending to IDE. For our second one, we've got Al, aluminum, and we find fluorine, but it's an ion, so we change the ending to IDE, aluminum fluoride. And our last one, K, potassium, and the Cl, chlorine, change the ene to ide, so chloride. Do we have questions on any of this so far?